So hello, welcome to algebraic geometry in East Asia seminar. I'm Young-Hoon Kim at KIAS. I recently moved from Seoul National University to KIAS actually last week. Today we have two great speakers on Donaldson-Thomas theory, and I think they will tell us about recent progresses in Donaldson-Thomas theory. So the first speaker is Dr. Tasuki Kinjo, and he will speak about homological Donaldson-Thomas theory for two Calabi-Yau categories. Okay, so
thank you.
Yeah.
Okay, thank you. Thank you so much for the introduction, and I'm very pleased to give a talk here. And the title is homological Donaldson-Thomas theory for two Calabi-Yau categories, but I want to change this a little bit. In today's talk, to simplify the exposition, I only consider the category coming from algebraic geometry. That is, we only work with the derived category of coherent shapes on the two Calabi-Yau surfaces. Okay, so let's start. In today's talk, we always work over the complex number field. Okay. And let me give an introduction. Okay. Let's see the smooth projective curve. And for simplicity, we assume the genus of C is greater than or equal, greater than or equal to 2. Okay, and now we give a definition of Higgs bundle. A Higgs bundle on the curve C is defined as follows. A Higgs bundle is a pair E phi where E is a vector bundle on C and phi is a morphism from E to E tensor product with its canonical bundle. And we say that a Higgs bundle is semi-stable if the following condition is satisfied. The degree of F divided by the rank of F is this degree of E divided by the rank of E. For all non-trivial here, sub-Higgs bundle is defined to be a sub-bundle of E, and phi F is the restriction of phi. Okay. So this is a definition of semi-stable Higgs bundle. Okay. Now we want to, oh, okay. Sorry, now let me give a remark on the definition of Higgs bundle. There is another way to define Higgs bundle. There is a bijective correspondence between Higgs bundles on C sorry, Higgs bundles on C and compactly supported purely one-dimensional coherent shifts on the total space of the canonical bundle. This bijection is called spectral correspondence, and this is a relative version of the fact that the category of finite dimensional vector space with its endomorphism and the category of compactly supported coherent shifts on A1. Okay. So we can define Higgs bundle to be a purely one-dimensional coherent shift on the total space of the canonical bundle. Okay. And now we consider the moduli space of semi-stable Higgs bundle, which is denoted by M Higgs R chi of C into this talk. This is a cos moduli space of semi-stable Higgs bundles E phi on C such that okay, and here is the simplest example of the moduli space of Higgs bundles. We first consider the case when R is equal to 1. In this case, it is clear that all Higgs bundles are semi-stable by definition. So this is a moduli space of all rank 1 and degree 0, Euler characteristic is equal to 0 Higgs bundles. And the moduli space of line bundles on C with Euler characteristic 0 can be identified with pic 0 of C. And the moduli space of Higgs field is nothing but the global section of the canonical bundle on C. Sorry. And here pic 0 of C is G-dimensional torus. And here, this affine space is also G-dimensional. In general, the moduli space is much more complicated, but looks somewhat similar to this. That is, in general, we cannot write the moduli space of Higgs bundle as a direct product, but it looks like a abelian variety product with an affine space. And we can show that the moduli space of Higgs bundles is smooth if and only if R are coprime. If R and chi are not coprime, the moduli space is singular along the strictly semi-stable locus. Okay. Now we define an affine space AR of C by the product of the global section of the canonical bundle powered by I. Okay, this is called the Hitchin base. And we define a very important morphism called the Hitchin fibration. This is a morphism from the moduli space of Higgs bundles to the Hitchin base. And this is denoted by HR and chi. And this morphism sends a Higgs bundle E phi to the tuple of trace of phi dot trace of phi powered by R. Okay. And here, several important properties of the Hitchin fibration. Firstly, HR chi, the Hitchin fibration is a proper surjective morphism. Okay. Secondly, we can show that this morphism is a completely integrable system, and hence the general fiber is isomorphic to an abelian variety. So for general P, in AR of C, the fiber is an abelian variety, and more strongly, we can say that we can show that it is a self-dual abelian variety. And this abelian variety is the Jacobian variety of the spectral curve corresponding to the Higgs bundle. Okay, and third property is for different choice of chi and chi prime, and for general P, the fiber of T by the morphism HR chi is isomorphic to HR chi inverse of HR chi prime inverse of P. So the situation is like this. So we have a kitchen base like this. And the general fiber is isomorphic to an abelian variety. And since this abelian variety is self-real, this is M Higgs of R chi of C, and this is M Higgs of R chi prime of C. So since these fibers are self-real and they are isomorphic, we can say that these spaces are mirror real in the sense of SYZ. So we can expect mirror symmetry phenomena for these spaces. Okay. And we have a topological mirror symmetry for these spaces. And there are many people who contribute to this theorem, but the blank is too small to list all the names, so I only write the name of merit here. So it was proved by several groups independently. Okay. Now assume that GCD of R and chi is equal to GCD of R and chi prime is further equal to 1. So these modular spaces are smooth. Then we have an equality of Hodge numbers. We have M Higgs of R chi of C is equal to HPQ of M Higgs of R chi prime of C. Okay. So this is a topological mirror symmetry statement for these spaces. Okay. So a natural question is what happens when we remove the assumption on the primarity? And in fact, we can show that when R and chi, the greatest common divisor of R and chi is not equal to the greatest common divisor of R and chi prime, then the cohomology group of these spaces are not isomorphic. And a natural alternative of the cohomology is intersection cohomology. So we can imagine if we use the intersection cohomology, then the statement is true, but actually this is not the case. We can show that the intersection cohomology does not satisfy the chi-independence phenomena or topological mirror symmetry phenomena. Okay. Here, IHD not 3. intersection cohomology group. So a natural question is, what is the correct cohomology theory for these spaces? Here, what I mean by correct is that it satisfies the topological mirror symmetry phenomena for all R and chi without coprimality assumption. And I will give an answer to this question in the last part of today's talk. Okay, so this is the introduction of my talk. So is there any questions so far? Okay, if there is no question, let's move on to the next topic. Okay. So now I want to explain what is cohomological Donaldson-Thomas theory. So let X be a Calabian threefold. Let X be a Calabian threefold. Here, in today's talk, Calabian threefold is defined to be a smooth threefold with trivial canonical bundle. And I do not assume the compactness of X. And let Mx be the moduli stack of compactly supported coherent shifts on X. Okay. And the following theorem is due to Joyce and his collaborators. But there are so many contributors and the blank is too small to write all the names. So I only write the name of Joyce. Okay. Firstly, what Joyce proved is MX is locally in smooth topology isomorphic to a critical locus. Here, critical locus is defined to be the locus where the differential of f is vanishing. And here, f is a function on a certain smooth space. So Joyce proves that the moduli stack of compactly supported coherent shapes on a Calabian threefold is locally isomorphic to a critical locus. And further, he showed that if this moduli stack is oriented, here I don't explain the definition of orientation because it's just technical condition, technical data. But so if we have an orientation then we can define a power shift which is locally isomorphic to the vanishing cycle complex. Here phi f is the vanishing cycle complex. Okay. And sorry. Cohomologicity theory is roughly a study of this power shift. Okay. And now I want to state the dimensional reduction theorem, which computes the hypercohomology of the above power shift in a certain situation. Let S be a smooth surface. And let pi be a projection. Okay, sorry. And let X be the total space of the canonical bundle on S. And by adjunction, X is a Calabian threefold. And let pi be the projection from mx to m of s, defined by push forward from x to s. Okay. Now we can see that mx carries a canonical orientation. So we can define the above power shift in this setting. And we can show that the push forward of Joyce's power shift to m of s is isomorphic to the dualizing complex of m of s shifted by the minus of the virtual dimension of m of s. Here, this is the dualizing complex. So by taking the hypercohomology, we have the hypercohomology of Joyce power shift is isomorphic to the Bremner homology of m of m of s. Here, the Bremner homology is defined to be the dual of the compactly supported homology of M of S. Okay. And here is the corollary of the dimensional reduction theorem. Now we assume S to be smooth Calabi-Yau surface. Such as K3 surface or abelian surface, or the total space of the chemical bundle on the Riemann surface, which corresponds to the Higgs bundle case. Okay. And we fix an ample divisor on S. And we consider an open substack MSS of P of S. This is an open substack of M of S defined by open substack parameterizing H semi-stable coherent shifts with reduced Hilbert polynomial is equal to P. And we define MSSP of X in the same manner. Then we have the hypercohomology of Joyce power shift on this open substack is isomorphic to the volume homology of MSSP of S. So this follows from the fact that the push forward from X to S preserves H semi-stability. Okay. So there is two ways to understand this theorem. First one is this theorem computes the cohomological Donaldson-Thomas invariance for local surfaces. And another point of view is that we can use cohomological DT theory for the study of the Bremner homology of moduli stack of objects, moduli stack of coherent shapes on surfaces. So a natural question, and one of the main theme of today's talk is, what can we say about the Bremner homology of this moduli stack using the above isomorphism? So we can interpret this Bremner homology group as a certain cohomologicality invariance. So what we can say using this statement. So this is a question here. Okay. So is there any question so far? Okay, let's move on to next. Okay, so firstly, we can define a multiplication on this volume homology group. And it was constructed by Kaplanov and Vasserov. We consider the following stack of extensions. This is moduli stack of extensions. Yes, this moduli stack parameterizes short exact sequence like this. And now we consider the following diagram. Here, sorry, here, EV of I denotes the ith evaluation map. Okay. And one can show that EV1 times EV3 is a locally complete intersection morphism. In derived geometric sense. Here, but I do not explain what does it mean by locally complete intersection in derived geometric sense, but what we only use is that we can refine the Gizim pullback along this vertical morphism. And one can also show that the second evaluation map is proper, which corresponds to the properness of the quad skin. So we can define the multiplication on the volume of homology group as follows. Okay, we first consider the volume of homology group of M of S, censoring with its copy, and we have the refined Gizim pullback along the vertical morphism. And then we have the proper push forward morphism along the horizontal morphism. And so we can define a multiplication on the volume of homology group. And this is called the Koha or cohomological Hall algebra multiplication. And this was introduced by Kaplanov and Vasserov. Okay. So we have a multiplication on the volume of homology group on the mosaic stack of coherent shapes on the surface. Now, we introduce a co-multiplication in the case of Calabi-Yau surface. And in the construction, we will use cohomological DT theory or Joyce power shift. And at present, we do not know how to construct it without using cohomological DT theory. Okay. Let S be a Calabi-Yau surface. And we define a preshift on the affine line whose name is dt over s, which encodes the sorry, and this preshift encodes the information on the cohomological DT invariance for surface S. And this preshift is defined as follows. The value of this preshift at an open subset U is the hypercohomology of M of S times U and phi of M of S times U. Here, M of S times U is a complex analytic open substack of M of S times A1. Okay, and the restriction morphism is defined by the natural restriction morphism of the power shift. Okay, and this preshift has the following property. And for a disk, D inside the complex plane, we have an isomorphism. DTS of D is by homotopy invariance isomorphic to DTS of the full complex plane, and by the dimensional reduction, this one is isomorphic to the volume homology of M of S. Okay. And for disjoint disks D1 and D2, the value of this preshift at D1 disjoint union with D2 is isomorphic to the volume homology of M of S tensoring with its copy. Okay, this theorem essentially follows from the Kinet theorem and from Sebastian theorem. Okay. So using these properties, we can define co-multiplication by considering the following diagram. Okay. We've considered a large, sorry, it's not a disk. We consider a large open disk, and we have two small open disks. Okay, and name the large open disk D1. Sorry. name large open disk by D, and name small open disks D1 and D2, and we consider the following restriction morphism: DTS of D to DTS of D1 disjoint union with D2. Oh, sorry, point in white color. So we consider this restriction morphism. Then by the first property, this one is isomorphic to the Bräumer homology of M over S. And this one is isomorphic to the Bräumer homology of M over S tensoring with itself. So we obtain a morphism from here to here. And this defines a co-multiplication on the Bräumer homology. Okay. And I want to remark here that we can define multiplication and co-multiplication for semi-stable moduli stacks. Multiplication and co-multiplication can be defined also for the Bräumer homology of M of semi-stable with fixed reduced Hilbert polynomial with the same construction. Okay. So we have multiplication on this Bräumer homology group for general surface S. And for Calabi-Yau surface, we can define coproduct using the homological invariant on S times A1. Okay, so now we can state the main theorem in the joint work with Davison. Okay. We let MSS of P of S to be the coarse moduli space of this stack. And now we assume S to be Calabi-Yau surface. And I also want to mention that the proof that this theorem can be extended to more general two Calabi-Yau categories. But for simplicity today, I only work with the case of Calabi-Yau surface. Okay, and let MSS P of S to be the coarse moduli space of this stack. And then we have a power sheaf called the BPS sheaf on this moduli space. with the following property. Here we use the following notation. We define the BPS cohomology of this space to be the hypercohomology of the BPS sheaf. Okay. The first property is that the BPS sheaf is the constant sheaf over the stable locus. Up to certain shift. And second, we can identify the primitive part of the polymer homology group of this stack with the BPS cohomology group adding a formal parameter of degree 2. Here, primitive part is defined to be for general coalgebra. The primitive part of A is defined by the locus where the product is as simple as possible. Okay. And the following statement is essentially equivalent to this statement by Milgram theorem. The polymer homology of this stack is isomorphic to the universal enveloping algebra of this Lie algebra. The BPS cohomology of the cosmology space, adding a formal parameter of degree 2. Here, this denotes the universal enveloping algebra. So this gives a structural result on the Kaplan-Bassel's cohomological whole algebra for two Calabi subspecies. That is, it is a universal enveloping algebra of some Lie algebra. Okay. Finally, let's move back to the first question about what is the correct cohomology theory for the moduli space of Higgs bundles. Okay. This is a theorem by myself and Naoki Koseki. So because that when S is a total space of the canonical bundle on a Riemann surface, the moduli stack of compactly supported coherent sheaves on the Calabi surface is isomorphic to the moduli stack of hex bundles on the original curve. So we can consider the BPS cohomology on the moduli space of hex bundles. Okay. And the theorem by myself and Naoki Koseki is that for chi, for different choices of chi and chi prime in C and R in the positive integer, we have an isomorphism of the BPS cohomology groups. So this statement says that if we use the BPS cohomology, we can show that the topological mirror symmetry statement without any assumption on R and chi. And finally, I also want to mention a theorem corollary by the work of Ben Davison and Lucien Hennecat and Sebastian Schlegel-Mezier. In their work, they give a structural result on the BPS cohomology group, and using their work and the above kind independence result, we can show that if GCD of R and chi is equal to GCD of R and chi prime, we have an isomorphism of the intersection cohomology group. Oh, sorry. So the topological mirror symmetry statement for the intersection cohomology group is true as long as this assumption is satisfied. Okay, thank you so much for listening. That's all for my talk.
Okay, thank you very much for the great talk. Are there any questions for Tatsuki Kinjo's talk? Or comments?
I have a question.
Yeah, please go ahead.
Yeah, hi, Tatsuki. Could you give some brief indication about the construction of the BPS cohomology, like, or maybe in some simple case or something?
I'm sorry, I couldn't listen well. So what of the BPS cohomology?
Sorry, could you give an indication of a brief idea about the construction of the HBPS? And also,
okay,
like what, yeah, I'm curious, like what kind of generality does this exist in? Is it something specific to this moduli space, or is it something we can construct more generally?
So this type of BPS cohomology or BPS shift is specific to the moduli space of objects in two trivial category. Okay, so we can write down the construction as follows. Okay, so let S be two trivial surface or moduli. Okay, let S be two trivial surface. And we consider the following diagram: MS2, MS2, Sorry, what I want to write. Mx to Mx. Maybe Ms. Here, X is a total space of the canonical bundle on S. And we consider the cosmology space. Here we consider a certain open substack of the two-moduli stack of coherent shapes on X and S, and we assume that there exists a cosmology space, and we name this Px and Ps and pi and pi bar. And so by the work of Joyce, there's a canonical power shift here, and the BPS shift is defined to be pi bar push forward of the first power piece of Px of push of phi of m of x shifted by -1. So the idea of the construction, this construction is due to Ben Davison and Equinoctoda, I think. And what I'm doing here is taking the first Pavas cohomology of this thing, this complex, and this operation corresponds to killing the equivalent parameter. So what we want to do is obtain a Pavas shift, so we need to kill the equivalent parameter. So we take the first Pavas truncation here, and then we take the push forward from this moduli space to the moduli space for S, and we take the shift by -1 to make it Pavas. So this is a construction of the BPS shift for two Calabi-Yau surfaces. And we can define the BPS shift for the moduli space of coherent shifts on Fano surfaces, but it is isomorphic to the intersection cohomology group on the stable locus.
So are there any other questions?
May I ask a question?
Yeah,
Hello?
sure.
Yes.
Sure.
So your statement is about co-multiplication about the Weimar homology, right?
Right.
Sorry. Yes. Can you formulate the shift level that do you also have co-multiplication on the good moduli space? I mean,
Yeah. So firstly, we have the. So yeah, if we assume the semi-stability, we can construct the co-multiplication at the level of the good moduli space, and more strongly, I think we can construct it at on the moduli stack. So we have a direct sum map on the moduli stack. So I think we have the morphism from this thing to dq of m of s to push forward of the dq of m of s tensoring with itself by the same construction. So yes, so there are two levels of generality. So we can construct it on the good moduli space, and we can also construct it on the moduli stack.
well, then finally you this statement to the like Quiver-Barty case, something like this.
Yeah, right. So yeah, essentially, so we can reduce this statement to the case of Quiver-Barty with several technical difficulty. Yeah, but essentially, yeah, we can reduce this to the.
But in order to reduce that, does you use the formality?
Yes.
Is that obstruction
Yes.
with generalizing your result to the Calabi-Yau case?
But formality is proved for general two Calabi-Yau category by Ben Davison. So the several technical difficulty is, for example, we need to check the BPS shift is compatible with analytic neighborhood theorem, and something like that. So they are not important essential technical difficulty, but yeah, we have this kind of difficulty in the proof.
I see. So formality is not a problem.
Formality is not a problem here.
Thank you very much.
So I also have a question for you.
Okay.
So does your BPS cohomology of the modular Higgs bundle has anything to do with the stringy E polynomial of Hausel-Tetius?
Yeah, that's a very good question. And at present, I don't know. But there should be, for example, if we consider the modular space of PGL Higgs bundle, I think we need to consider something like a mix of BPS cohomology and the stringy E polynomial in order to state the topological Miller symmetry statement for non-prime around chi. And so, yeah, I think it is a very very good question. It is a very important problem to understand what is the relation between the BPS cohomology and stringy E polynomial to formulate the topological Miller symmetry statement for arbitrary reductive groups. Thank you so much for the question.
Oh, thank you. Thank you. So, okay. So any other questions or comments? So if not, I'd like, let's thank Dr. Kinjo for his wonderful talk. Okay, so we'll take a break for 7 minutes, and the second talk will start at 5:15. Okay, thank you. Thank you, Kinjo.
Thank you so much.